Imagine for a moment that you are a young aeronautical engineer in the late 1930s. You've just presented what you consider to be the most revolutionary military aircraft design ever conceived, a twin-engine fighter with a completely new configuration, capable of unimaginable speeds and a range that would change the rules of aerial warfare. But when you finish your presentation, all you receive is silence, skeptical faces, looks of disbelief. And then the words no innovator wants to hear: "That will never work." This is the story of Clarence Leonard Johnson, known simply as Kelly Johnson, and how his impossible design became one of the most feared weapons in the sky during World War II. A story of rejection, perseverance, and how a single man changed the course of military aviation forever. Because what you're about to discover isn't just about one plane. It's about how the best ideas often come from those who refuse to accept that something can't be done. Before we continue this fascinating journey, subscribe to the channel and comment below what time you're watching this video. Let's get started. Burbank, California, 1937. Lockheed Aircraft Corporation was at a crossroads. The company had survived the difficult years of the Great Depression, but barely. Its competitors, giants like Boeing, Douglas, and Curtiss, dominated military contracts. Lockheed needed something revolutionary, something that would put it back in the game. And it was in this moment of corporate desperation that the United States Army Air Corps issued a specification that seemed impossible to meet. The specification was known as the X-608, and it called for something never before. The Army wanted a high-altitude interceptor, capable of reaching 360 miles per hour at 20,000 feet, with the ability to fly for at least an hour at that speed. More than that, the aircraft needed to have an impressive initial climb, reaching 20,000 feet in just 6 minutes. And all of this had to be packaged in an airframe reliable enough for intensive military operations. To understand how absurd this sounded at the time, you need to consider the context. Fighters of the era, like the Boeing P-36 pea shooter, could barely exceed 230 miles per hour. Most American military aircraft were still biplanes with wood and fabric structures. The idea of a fighter capable of 360 miles per hour seemed more like science fiction than real aeronautical engineering. But there was one man at Lockheed who looked at that specification and saw not an impossibility, but an irresistible challenge. Kelly Johnson was only 27 years old, but he had already proven himself to be an aerodynamic genius. Born in Michigan to Swedish immigrants, Johnson had fallen in love with airplanes as a child. The story goes that at 13, he built his first model aircraft and became obsessed with understanding why it wouldn't fly correctly. This insatiable curiosity would lead him to the University of Michigan, where he earned a degree in aeronautical engineering. Johnson had joined Lockheed in 1933 and quickly gained a reputation for being brilliant but difficult. He had no patience for corporate politics or doing things the way they've always been done. Johnson questioned everything, challenged established assumptions, and frequently clashed with older engineers who saw his radical ideas as the fantasies of an arrogant young man. When the X-608 specification reached Johnson's desk, he immediately realized that conventional methods wouldn't work. One engine simply wouldn't provide enough power to reach the required speeds. The obvious solution would be to use two engines, but this created a completely new problem. Twin-engine aircraft of the time were large, heavy, and slow. How could you create a twin-engine fighter that was both fast and agile? Johnson spent weeks crunching numbers, sketching designs and testing concepts in makeshift wind tunnels. And then late one night in the Lockheed design office, he had a vision that would change everything. What if instead of placing the engines in the wings as was conventional, he placed them in two long distinct nacelles with the propellers in front? What if he connected these nacelles to a short central fuselage where the pilot would sit? And here's the truly radical part. What if he added a twin tail connecting the engine nacelles? When Johnson presented his concept to Lockheed's superiors, the reaction was exactly what you'd expect. "It looks like a fork," said one executive, shaking his head. "It'll never be stable in the air," insisted another senior engineer. "You're asking us to build an aircraft that challenges everything we know about fighter design." But there was something about Johnson's design that was undeniably elegant. The twin-tail configuration was not only unusual, it was aerodynamically brilliant. It would provide exceptional stability, and allow the center fuselage to remain short and light. The engine nacelles would create streamlined bodies that would actually contribute to the aircraft's overall lift, and centralizing all the weapons in the fuselage meant the pilot could aim and fire, without having to compensate for the convergence of wing-mounted weapons. But the most controversial aspect of Johnson's design was the engine selection. He specified the new Allison V1710 turbocharged engines. These engines were promising but unproven. Many at Lockheed felt that betting on untested technology was too risky. Johnson argued that turbochargers were essential. They would allow the engines to maintain power at high altitudes, exactly what the X608 specification required. Internal politics at Lockheed were brutal. Johnson had allies, including Chief Engineer Hall Hibbard, who recognized the young engineer's brilliance. But he also had enemies, people who saw his unorthodox ideas as threats to the established order. There were heated meetings, angry memos, and veiled threats that Johnson's career at Lockheed could end if he continued pushing for his impossible design. But Johnson had something his critics didn't: an unshakable confidence backed by solid mathematics. He had run the calculations dozens of times. He knew his design would work. He just needed a chance to prove it. Finally, in June 1937, Lockheed decided to take the plunge. The company submitted Johnson's design to the Army Air Corps. The proposal, called the Model 22, promised not only to meet the X608 specifications, but to significantly exceed them. Lockheed claimed the aircraft would reach over 400 miles per hour, have a range of over 1,000 miles, and could operate at altitudes exceeding 30,000 feet. The Army was intrigued but skeptical. The design was so radical, so unlike anything tried before, that many officers simply didn't believe it could work. But war was looming on the horizon. Nazi Germany was aggressively rearming. Intelligence reports suggested the Germans were developing advanced fighters that would render existing American aircraft obsolete. The United States needed something innovative and fast. In June 1938, after nearly a year of analysis and debate, the Army did something extraordinary. They awarded Lockheed a contract to build a prototype Model 22. But there was a cruel catch. Lockheed had to build and fly the prototype within 6 months, and do so entirely at its own expense. If the plane failed, Lockheed would absorb the stall. It was a huge financial risk for a company still recovering from the Depression. Johnson and his team worked at a frantic pace. They faced hundreds of technical challenges no one had encountered before. The twin-tail configuration created control issues that required innovative solutions. The turbochargers proved temperamental and difficult to integrate. The landing gear had to be exceptionally strong to support the weight of a twin-engine aircraft, yet light enough to not compromise performance. There were moments of profound despair. Wind tunnel tests revealed unexpected buffeting problems that threatened to make the aircraft unstable at high speeds. Johnson's solution was to redesign the tail sections, adding small fillets that smoothed the airflow. It was one of hundreds of small adjustments that transformed a promising concept into a viable aircraft. On January 27, 1939, the prototype, now designated XP-38, was trucked to March Field in California. The aircraft was impressive to behold. Its twin-tail design gave it an almost alien appearance. The short central fuselage, with its prominent glass cockpit, seemed disproportionately small between the massive engine nacelles. Many onlookers thought it looked fragile, as if it might disintegrate in mid-air. The test pilot chosen for the first flight was Ben Kelsey, a lieutenant in the Army Air Corps. Known for his exceptional skill and steely nerves, Kelsey examined the aircraft carefully, asking Johnson detailed questions about every system, every design quirk. Johnson answered everything with the confidence of someone who knew every screw, every electrical circuit, every control surface. The first flight was scheduled for a cold, clear morning. When Kelsey started the engines, the roar was unlike anything anyone had ever heard from a fighter jet. It was deeper, more powerful, almost menacing. The aircraft taxied to the runway, the Allison engines singing in perfect harmony. And then, with a ground-shaking roar, the XP-38 accelerated down the runway. What happened next entered aviation legend. The aircraft didn't just take off. It leapt into the air with an agility that defied its size. Kelsey would later recount that he knew immediately he had something special on his hands. The aircraft responded to the controls with remarkable precision. It was fast, incredibly fast, even with the engines not yet fully tuned. During subsequent test flights, the P-38 proved to be everything Johnson had promised and more. It reached speeds exceeding 400 miles per hour, becoming one of the fastest aircraft in the world. It climbed to altitudes that most fighters of the time could not reach. And, most importantly, it was stable and controllable in all phases of flight. But the real test came in February 1939, when the Army decided to stage a dramatic public demonstration of the aircraft's capabilities. They ordered Kelsey to fly the P-38 coast to coast, setting a new transcontinental speed record. It was a risky mission. The aircraft was still a prototype, with systems not fully tested. A failure on such a public flight would be disastrous for Lockheed and the program. On February 11th, Kelsey took off from March Field in California, bound for Mitchell Field in New York. The flight was spectacular. The P-38 crossed the continent in just 7 hours and 48 minutes, setting a new record and capturing headlines across the country. The aircraft proved itself not only fast, but also reliable enough for long-distance travel. But then fate intervened in a cruel way. During the landing approach at Mitchell Field, the engines failed. Kelsey attempted to glide to the runway but lost altitude. He was forced to make an emergency landing on a golf course, and the prototype was destroyed. Miraculously, Kelsey emerged unharmed. But the only P-38 in existence was now a twisted mass of metal. For many at Lockheed, it felt like the end. Years of work, millions of dollars, all destroyed in an instant. Johnson's critics saw the accident as validation of their concerns. "I said the design was too radical," one executive was heard saying. "Maybe we should have followed more conventional methods." But the accident investigation revealed something crucial. The engine failure had nothing to do with Johnson's design. It was caused by a fuel system problem, something completely separate from the innovative fuselage configuration. In fact, the plane had flown magnificently up until the moment of mechanical failure. And more importantly, the transcontinental flight had proven, beyond a shadow of a doubt, that the fundamental concept was correct. The Army Air Corps was impressed enough to do something unprecedented. Despite the loss of the prototype, they placed an order for 13 production aircraft in April 1939. It was an extraordinary vote of confidence in Johnson's design. The production aircraft would be designated the P-38 Lightning, a name that would soon become synonymous with air superiority. But transforming the prototype into a production aircraft proved almost as challenging as creating the original design. Johnson discovered that making an aircraft work once was completely different from making hundreds of them work reliably. Each system had to be refined, tested, and refined again. Lockheed had to build entirely new tooling and manufacturing processes to produce the P-38's unique configuration. One of the most significant challenges involved the turbochargers. These devices were essential to the P-38's high-altitude performance, but they were notoriously temperamental. They operated at extreme temperatures and pressures and were prone to failure. Johnson and his team spent months developing reliable control systems and maintenance procedures. Each turbocharger had to be carefully tuned to work in harmony with its engine and the aircraft's other turbocharger. Another problem was what became known as compressibility. As the P-38 approached its maximum speed in high-speed dives, pilots began to experience a frightening phenomenon. The controls would become stiff, nearly impossible to move. The aircraft would begin to shake violently. In some cases, pilots lost control and were killed. This was something completely new, a problem no other fighter had encountered simply because no other fighter was fast enough. Johnson realized that the P-38 was experiencing the effects of transonic speed, something poorly understood in aeronautical theory at the time. As the aircraft approached the speed of sound, the airflow over certain parts of the fuselage actually exceeded the speed of sound, creating shock waves that disrupted control. The solution involved adding hydraulically operated dive flaps under the wings. These flaps could be extended during high-speed dives, creating drag that kept speed within controllable limits. While these technical problems were being resolved, the global situation was rapidly deteriorating. In September 1939, Germany invaded Poland. Starting World War II, the German Luftwaffe demonstrated revolutionary aerial warfare tactics, using fast and maneuverable Messerschmitt fighters to dominate the skies. It became painfully clear that the United States was years behind in fighter technology. The P-38 suddenly became not just a worthwhile project, but a national priority. The Army dramatically increased its orders. Lockheed had to expand its production facilities almost overnight. Johnson found himself overseeing hundreds of engineers and thousands of workers, all working around the clock to get P-38s into the air. The first operational P-38s began arriving at Army Air Corps units in 1941. Pilots had mixed reactions. The P-38 was arguably the most complex fighter any of them had ever flown. It had 2 engines to manage, turbochargers to monitor, and a multitude of systems that required constant attention. But once they mastered its intricacies, pilots fell in love with the aircraft. The P-38 had advantages no other fighter could match. Its exceptional range meant it could escort bombers on missions deep into enemy territory. Its speed and rate of climb allowed it to intercept enemy bombers at high altitudes, where other fighters could not operate effectively. And its armament, 450 caliber machine guns and a 20mm cannon, all concentrated in the nose, provided devastating firepower. When the United States entered the war after Pearl Harbor in December 1941, the P-38 was quickly deployed to all theaters of operation. In the Pacific, it proved particularly valuable. The vast distances over the ocean required a fighter with long range, something single-engine fighters simply could not provide. The P-38 could escort bombers across New Guinea, patrol over hundreds of miles of ocean, and reach targets previously beyond the reach of Allied fighters. But it was in Europe that the P-38 truly made its name as a Luftwaffe nightmare. German pilots, accustomed to dominating the skies with their Messerschmitts and Focke-Wulfs, suddenly found themselves facing an adversary that could outmaneuver them, outperform their rate of climb, and unleash a volume of fire that was simply terrifying. The P-38's distinctive twin-tail configuration became instantly recognizable. Luftwaffe pilots called it der Gabelschwanzteufel, the forked-tailed demon. There was something psychologically intimidating about the P-38. Its unusual design made it seem alien, almost otherworldly. When one appeared on the horizon, German pilots knew they were facing not just another aircraft, but the embodiment of American ingenuity and industrial might. And it wasn't just the look. It was the sound. The twin Allison engines created a deep pulsing note unlike any other aircraft in the sky. You could hear a P-38 coming before you saw it. One of the most famous missions involving the P-38 occurred in April 1943. American intelligence had intercepted and decoded Japanese messages revealing that Admiral Isoroku Yamamoto, the commander-in-chief of the Imperial Japanese Navy and architect of the attack on Pearl Harbor, was making an inspection trip to the Solomon Islands. It was an unprecedented opportunity to eliminate one of Japan's most important military leaders. The problem was that Yamamoto's flight would be more than 400 miles from the nearest Allied base. No fighter except the P-38 had the range to make an interception. 16 P-38s from the 339th Fighter Squadron were selected for the mission. They flew at wave height for nearly 2 hours to avoid radar detection, then climbed to intercept the Mitsubishi bombers carrying Yamamoto and his team. The mission was a complete success. The P-38s shot down Yamamoto's bomber, killing him. It was a devastating blow to Japanese morale and demonstrated the P-38's unique range and capabilities. No other Allied aircraft could have accomplished that mission. As the war progressed, the P-38 continually evolved. Johnson and his team at Lockheed constantly refined the design, incorporating lessons learned in combat. Later versions had more powerful engines, greater fuel capacity, and improved armament. The P-38L variant, introduced in late 1943, was significantly more capable than the original models. But perhaps the P-38's most significant legacy was not military, but cultural and technological. Johnson's design proved that radical innovation could work, that challenging conventional wisdom could lead to breakthroughs. The twin-tail configuration, once considered eccentric, inspired countless subsequent designs. The turbochargers Johnson championed became standard on high-altitude aircraft. Lessons learned about compressibility and transonic flight paved the way for the next generation of jet fighters. And for Kelly Johnson personally, the P-38 was just the beginning. His innovative design approach and willingness to take technical risks became his trademark. He would go on to lead the development of some of the most iconic aircraft in aviation history. The P-80 Shooting Star, America's first operational jet fighter. The F-104 Starfighter, a supersonic interceptor that set numerous speed and altitude records. And perhaps most famously, the SR-71 Blackbird, a reconnaissance aircraft that remains the fastest manned aircraft ever built. Johnson would go on to found Lockheed's Skunk Works division, a secretive operational unit that became legendary for developing some of the world's most advanced and secret aircraft. But it all began with that rejected design in the late 1930s. A young engineer who refused to accept that something couldn't be done. An aircraft everyone said would never work. And a legacy of proving the skeptics wrong. By the end of World War II, more than 10,000 P-38s had been built. They served in every theater of operations, from the North African desert to the jungles of the Pacific, from the icy skies of Scandinavia to the plains of Eastern Europe. P-38 pilots claimed thousands of aerial victories. The aircraft set countless records. But more than statistics, the P-38 represented something fundamental about innovation and progress. It represents what happens when you give someone brilliant the freedom to challenge assumptions. When you're willing to take risks on unconventional ideas, when you persist even when everyone tells you you're wrong. The story of the P-38 is a story about a man, but it's also a story about a culture, an organization and a nation willing to embrace the radical and the new. Think about that for a moment. In 1937, Johnson's design was dismissed as impossible by nearly everyone who saw it. Just 6 years later, in 1943, it was considered indispensable. Luftwaffe pilots feared it. Allied generals planned entire campaigns around its capabilities. It had gone from a rejected idea to a defining weapon of war in less than a decade. And this raises a fascinating question. How many other impossible ideas are being rejected right now? How many other Kelly Johnsons are presenting radical designs only to be met with skepticism and disbelief? How many potentially world-changing innovations are being dismissed because they challenge conventional wisdom? The story of the P-38 teaches us that the best ideas often seem the worst at first. They challenge fundamental assumptions. They require people to think in completely new ways. They are uncomfortable, unsettling, even frightening. But it's these ideas, the ones everyone says won't work, that end up changing everything. Kelly Johnson lived by a philosophy he would summarize later in his career. He called it the KISS principle. Keep it simple, stupid. But Johnson's simplicity wasn't about avoiding complexity. It was about eliminating unnecessary things, about finding the most elegant solution, not the most obvious. The P-38, with its radical configuration, was actually a simpler aircraft in many ways than more conventional designs. Every element served a purpose. There was nothing superfluous. This philosophy permeates the entire history of the P-38. When Johnson decided to use twin engines, it wasn't because he wanted to make the aircraft more complex. It was because physics dictated that a single engine couldn't provide enough power. When he created the twin-tail configuration, it was no different. It was because it was the most elegant solution to the stability and control problems that a twin-engine fighter airframe created. Every radical design decision had a solid engineering justification behind it, and this is crucial to understanding why the P-38 succeeded when so many other radical designs failed. Johnson wasn't being radical for the sake of being radical. He was solving real problems with innovative solutions based on sound physics and mathematics. There was substance behind the style. There was science behind the boldness. Pilots who flew the P-38 in combat developed a deep appreciation for these design choices. So initially, many complained about the complexity of managing 2 engines, 2 turbochargers, and all the interconnected systems. But in the heat of combat, they realized the advantages. If one engine was hit, the other could bring them home. The turbochargers, temperamental as they were, allowed them to fight at altitudes where enemy fighters could barely operate. The twin tails provided stability that made the aircraft an incredibly accurate weapons platform. There were stories, hundreds of them, of pilots returning home in severely damaged P-38s, aircraft with one engine completely destroyed, flying the 300 miles back to base with only one engine working, aircraft with large wing sections ripped off by anti-aircraft fire, still controllable, thanks to the inherent stability of the twin-tail design. The P-38 was robust in ways that single-engine fighters simply could not be. And then there was the intimidation factor. This may seem superficial, but it wasn't. In aerial warfare, psychology matters. When German pilots saw those characteristic twin-tail silhouettes approaching, they knew they were facing adversaries with every advantage. The P-38s were faster, could climb higher, and had more range. The pilots flying them were typically well-trained and well-rested Americans, as opposed to the increasingly tired and poorly fueled Germans by the end of the war. The Germans developed specific tactics for dealing with P-38s, which in itself is a testament to their impact. They instructed pilots to avoid prolonged combat, employing quick attacks and escapes. They recognized that in a prolonged fight, the P-38's advantages in speed and firepower would make it nearly impossible to defeat. But here's something fascinating that's often overlooked in the P-38's history. It wasn't perfect. It had real significant flaws. And how Johnson and his team addressed those flaws is as important as the original design. One of the most persistent problems was cabin heat, or rather, the lack thereof. The P-38's configuration placed the pilot far from the engines, which meant there was very little heat source for the cabin. This wasn't a problem in the Pacific or North Africa, but in Europe, where P-38s often operated at 30,000 feet where temperatures dropped to minus 50 degrees, it was agonizing. Pilots suffered from frostbite. Some lost fingers and toes. It was a serious problem that affected operational effectiveness. Johnson tried various solutions: electric heating systems, hot air ducts for the engines, better pilot clothing. Nothing worked perfectly. It was a humbling reminder that even the most brilliant designs have limitations, that innovation is an ongoing process, not a one-time event. Another problem arose in combat. Centralizing all the weapons in the nose while providing exceptional accuracy also created a vulnerability. If the nose was hit, all weapons could be destroyed simultaneously. Fighters with wing-mounted weapons had redundancy. A round could destroy the weapons on one wing, but those on the other wing would still function. The P-38 didn't have that luxury, and there were low-altitude maneuverability issues. While the P-38 excelled at high altitudes, in low-altitude combat against agile enemy fighters, like the Focke-Wulf 190, it was at a disadvantage. It was simply heavier and had greater inertia. It couldn't turn as tightly or roll as quickly as some of its adversaries. The pilots learned to fight within the P-38's forces. They utilized its superior speed and rate of climb. They avoided prolonged low-altitude dogfights. They picked their battles, getting in fast, attacking with devastating firepower, and getting out before enemy fighters could respond effectively. It was a matter of playing to their strengths, not their weaknesses. And this brings us to another crucial lesson from the P-38 story. There is no such thing as a perfect design. Every aircraft, every product, every innovation involves compromises. You optimize for certain capabilities while accepting limitations in other areas. Johnson's brilliance wasn't in creating a perfect aircraft. It was in creating an aircraft whose strengths dramatically outweighed its weaknesses, and whose unique capabilities filled critical gaps that no other aircraft could. The long-range escort role was where the P-38 truly shined. Before the P-38 and later the P-51 Mustang, Allied bombers raiding deep into Germany had no fighter escort. They were slaughtered by Luftwaffe fighters. The losses were unsustainable. But the P-38 changed the equation. Suddenly, the bombers had protection throughout the mission. German fighters, which had previously been able to attack the bombers with impunity, now had to fight through screens of P-38s. This fundamentally changed the strategic bombing campaign. It allowed the Allies to sustain large-scale bombing raids that destroyed Germany's industrial capacity. Factories, oil refineries, transportation networks, everything became vulnerable, and the P-38 was instrumental in making this possible. One mission in particular exemplifies the P-38's impact. In August 1943, the 8th Air Force launched a massive attack on the ball-bearing factories in Schweinfurt and Regensburg, Germany. These were critical targets. Destroying them would be a devastating blow to German war production. But they were deep inside Germany, beyond the range of most escort fighters. The P-38s pushed themselves to the limit of their range, fighting off waves of German interceptors. When they finally had to turn away due to fuel shortages, the bombers remained unescorted. What followed was a massacre. The Luftwaffe shot down 60 bombers. It was one of the worst losses the 8th Air Force had ever suffered. But significantly, while the P-38s were present, losses were minimal. It was a painful testament to how critical long-range escort had become. Missions like this led to further improvements to the P-38. Larger external fuel tanks extended its range even further. Improved radio systems improved coordination with bombers. Each combat lesson led to refinements, adjustments, and incremental improvements that made the aircraft increasingly effective. And then there were the pilots, the men who transformed Johnson's brilliant design into an effective weapon of war. Pilots like Richard Bong, who became the highest-scoring American ace in history with 40 confirmed victories, all in a P-38, or Thomas Maguire with 38 victories, also all in P-38s. These men didn't just fly the aircraft, they mastered it, exploiting every capability, compensating for every limitation. Bong, in particular, developed tactics that became legendary. He used the P-38's superior speed to dictate the pace of the fight. He would dive from high altitudes, attack with a devastating burst from his 4 machine guns and cannon, then use his momentum to climb back to safe altitude before enemy fighters could react. He was brutal, efficient, and terrifyingly effective. But here's what's truly remarkable about the P-38 story. It wasn't just about the airplane. It was about the entire system surrounding it. Johnson's design genius was crucial, but so was Lockheed's innovative manufacturing, pilot training, battlefield maintenance, and continuous improvement based on combat experience. It was a complete ecosystem of innovation and excellence. Lockheed developed mass production techniques that were revolutionary for the time. They created specialized tools that allowed relatively inexperienced workers to produce precision components. They implemented rigorous quality controls to ensure reliability. They established supply lines that kept production flowing even when critical materials were scarce due to wartime demands. And they listened. This is perhaps the most crucial aspect. Johnson and his team maintained constant contact with combat units. They read mission reports, interviewed pilots, and analyzed damaged aircraft returned. Every piece of information from the front was an opportunity to improve. It wasn't a "we build it, you fly it" mentality. It was a collaborative partnership between designers, manufacturers, and end users. This approach led to innovations that would never have occurred in the isolation of a drawing board. For example, pilots reported that glare from the cockpit glass sometimes blinded them in certain sunlight angles. Lockheed's solution was to redesign the glass panels with an anti-reflective coating. Small adjustment, big impact on operational efficiency. Or consider the problem of short runway takeoffs. In the Pacific, many airfields were hastily constructed dirt runways on captured islands. The P-38, being a large and heavy aircraft, sometimes struggled to take off over short distances when fully loaded. The solution involved fine-tuning flap settings and developing improved takeoff techniques. Again, small adjustments that made a big difference in operational effectiveness. As the war drew to a close, the P-38 began to be replaced in some roles by the P-51 Mustang, which had even greater range and was less complex to maintain. But the P-38 never became obsolete. It continued to serve with distinction until the last day of the war, particularly in the Pacific, where its unique capabilities were invaluable. And after the war, the P-38's influence continued. Many of the lessons learned during its development informed the next generation of military aircraft. Understanding high-speed flight, developing reliable turbocharger systems, and manufacturing techniques all became part of the aviation body of knowledge. Kelly Johnson would continue to lead innovation at Lockheed for decades. He would develop more than 40 different aircraft during his career. But he always had a special place in his heart for the P-38. It was his first major victory, proof that his radical ideas could work. Years later, he would describe the P-38 as the aircraft I'm most proud of, and rightly so. The P-38 wasn't just a successful aircraft. It was a statement, proof that radical innovation was possible, that challenging conventional wisdom could lead to breakthroughs, that persisting in the face of skepticism could change the world. Think about the journey. A young 27-year-old engineer with a radical idea, skeptics everywhere saying it would never work, a prototype that crashed on a golf course. And then, just a few years later, thousands of these impossible aircraft dominating the skies, changing the course of the war, saving countless lives. It's a story of courage. Johnson's courage to stand up for his ideas, Lockheed's courage to bet on them, the courage of the pilots who flew a radical, untested aircraft in combat, the courage of the nations who entrusted their lives and freedom to this unproven innovation. But it's also a story about humility, about recognizing that no design is perfect, about being willing to learn from mistakes, to listen to criticism, to continually improve. Johnson never pretended the P-38 was perfect. He openly acknowledged its flaws and worked tirelessly to address them. And it's a story about collaboration. No single person created the P-38. Johnson had the vision, but a team of engineers realized it. Factory workers built it, pilots tested and refined it. Maintenance crews kept it flying. Military commanders employed it effectively. Success was the result of thousands of people working together toward a common goal. In today's world, where innovation is a buzzword, where everyone claims to be disruptive, the story of the P-38 offers important lessons. Real innovation is hard. It's not about having crazy ideas. It's about having ideas that challenge assumptions, but are grounded in solid physics, rigorous mathematics, and a deep understanding of the problems you're trying to solve. Real innovation encounters resistance. If everyone loves your idea immediately, it's probably not radical enough. The best ideas make people uncomfortable because they challenge the way they've always done things. You have to be prepared to face skepticism, criticism, even ridicule. And you have to have the confidence and data to persevere. Real innovation requires iteration. The XP-38 that flew in 1939 was significantly different from the P-38L that ended the war. There were hundreds of modifications, thousands of small improvements. Innovation isn't a one-time event. It's a continuous process of refinement and improvement. And real innovation has impact. It's not enough to create something new. You have to solve a real problem. You have to make a measurable difference. The P-38 wasn't interesting because it looked cool or because it was technically impressive. It was important because it fundamentally changed what was possible in aerial warfare. It saved lives. It altered the course of history. When you think about it this way, the story of the P-38 transcends aviation. It's a story of human courage, ingenuity, and determination, about facing seemingly impossible problems and refusing to give up until solutions are found, about turning rejection into triumph. And it's a reminder that progress isn't inevitable. It doesn't happen on its own. It happens because courageous individuals, people like Kelly Johnson, are willing to risk their careers and reputations on ideas everyone else dismisses. It happens because organizations like Lockheed are willing to invest resources and support. It happens because societies are willing to embrace change and innovation. Ultimately, the P-38's legacy isn't just about an aircraft. It's about what's possible when we combine vision, determination, and excellence. It's about how one person with an idea can change the world if they have the courage to persevere, when everyone says it's impossible. So the next time you face a seemingly impossible problem, think of Kelly Johnson. Think of that young 27-year-old engineer staring at a specification everyone said couldn't be met. Think of him sketching an aircraft everyone said would never fly. Think of him persisting through rejection, skepticism, even a prototype falling apart. And then think of P-38s tearing through the sky over Europe and the Pacific, their twin engines roaring, their unmistakable twin tails, Luftwaffe pilots diving to escape the forked-tailed demon. Think of all the lives saved, all the missions completed, all the impossibles made possible. Because that's the true lesson of the P-38 Lightning. The impossible is only impossible until someone proves otherwise. And often, that person is someone everyone underestimated, someone whose idea everyone rejected, someone who refused to accept that something couldn't be done. Kelly Johnson proved them wrong, and in doing so, he not only created one of the most iconic aircraft in history, he showed us that the biggest obstacle to innovation isn't technology. It's not physics. It's not engineering. It's the belief that something can't be done. Break that belief and you can change the world, just as one young engineer did with a design everyone rejected, which became a nightmare for enemies and a symbol of hope for those fighting for freedom. This is the story of the P-38 Lightning, and it's a story that continues to inspire more than 80 years later. May the Lord God bless each of you who watched until the end. May He inspire in your hearts the same courage and determination we saw in Kelly Johnson's story. May you never give up on your dreams, even when everyone says it's impossible. Because with faith, hard work, and perseverance, the impossible becomes possible. May God be with you, and until the next inspiring story,